So, I'm a mathematician, and I think you guys all know that. But what's the deal with these statisticians? I mean, they're all over the place. I was walking by the river once, I saw a statistician by the river too, and all of a sudden he jumps into the river. And he starts walking through, and then starts flailing. He's drowning. I have to run in there after him and pull him back. He said, "What's going on? That's crazy. Why would you jump in that river?" He said, No, it was fine. I calculated that it was 3 feet deep on average. And another thing about these statisticians, they always need a full set of data. They say, if you don't have enough data, then I can't work with it. And I look at them and I say, there are two kinds of people in this world. Those who can extrapolate from insufficient data.
All right, we are back. Let's get into it. So this week is relatively easy. I hope everyone saw the practice exam online, and hopefully you take it before at least you take the actual exam come the end of this week. And I'll be going over a review on the Wednesday's video, but of course you're able to watch that whenever you want. Today's topic is actually a relatively easy one. I think so anyway. It's simply called evaluating definite integrals. And you guys have already done that, so this is maybe a better way of talking about this is saying getting better at evaluating definite integrals. And there are some techniques that maybe you want to keep in mind, and other properties that maybe you haven't seen before with definite integrals. So we'll get started, and the book likes to bring up just a list of rules. This is just like a list of properties, just like with the indefinite integrals that you guys already did a week ago now. Actually, it gets longer than that even. Properties of the definite integral. And it lists 5 of these. And I'm pretty sure you could agree with me on most of these right away, but maybe some of them are going to need a little bit more work. So this first one, if I'm integrating a definite integral from a point A to that same point A, this is going to be 0. I think you should all be able to figure out why, but the question is why. Okay, how much area is under the curve? And I think everybody would say 0. So that's why, the amount of area between A and A. Another way you can think about that is also as an antiderivative. F of A minus F of A is also 0. So either way, you want to think about that. If you're integrating from a point to itself, it's definitely 0. Second property is if I'm going from one point to another point, I'm going from A to B, and suppose I flip that around. Suppose I decide to go from B to A instead. Then what I get is a minus sign. And this one comes directly from the antiderivative notation. This is f of B minus f of A equals exactly negative f of A minus f of B. That's why. So you would just write it out using that fundamental theorem of calculus. Number 3, says, this is what we've already seen with indefinite integrals, so it better still be true. If I have a constant that I'm multiplying by my function, I can pull the constant out front, and I think all of you guys were already doing this for your homework. So don't worry too much about that. I'm not going to explain why. Number 4. Also something that we've already encountered with indefinite integrals. F of x plus or minus, right? Either one of these is the same. If I'm adding or subtracting another function, I can split the integral up at the plus or minus sign. And so the reverse of this could also be true, but you'll notice that the bounds have to be the same there. So if I had 2 separate integrals, I could combine them into one as long as the bounds are the same. I'm not going to prove that. It follows directly from indefinite integrals. Number 5, though, this is kind of a new one. This is interesting. So if A is less than B is less than C, then I wonder if you can hear my cat in the background. She sounds tortured. Poor girl. She really likes attention, that's why. Maybe I'll bring her in one of my videos one of these days. She can say hi to all of you. If A is less than B is less than C, then actually you can add definite integrals in the right way. So I'll show you what that means. A to B f of x dx plus b to c f of x dx equals the integral from a to c f of x dx. And there are a couple ways of proving this, so I'll just say 2 proofs. The first is just doing it with the antiderivative. So the first integral would look like, if I'm going from a to b, this is f of b minus f of a plus, and now the second integral is f of c minus f of b. And you'll notice, what do I have here? Well, I have a positive f of b. Circle that. I have a positive f of b right there, and I have a negative f of b right there. So actually the f of b's cancel, and I'm left with really an f of c on the right side minus f of a on the left side. And that's exactly what you expect. I wonder if you can hear my cat, that poor girl. I'll bring her in 1 second. Jill, come here. Okay. She gets really excited when it's springtime because she wants to go outside, but we don't let her outside anymore. We have a leash for her, but she doesn't like the leash either. Okay, so that's proof number 1. Proof number 2, we can talk about adding areas together. So if I want to talk about adding areas together, what's really going on here? Well, suppose I have some curve. Looks like that. Suppose there's A, there's B, and there's C. If I start by looking at the area between A and B, that's this area, and I add that area to the area between B and C, then what do I have? I just have the total area. So you can also think about it that way. So yeah, this is kind of nice because it means that you can split them at bounds, or you can add them together at bounds, as long as those bounds line up. Basically, what you want to keep in mind is that the bottom number of one is the top number of the other, and then you can add them together. You basically Okay, so let's just try one of those cases, this last case, see if we can figure out how it works. The real reason why we use the last case is piecewise functions. So you'll remember we've been working with continuous functions for so long that it's going to feel like piecewise functions don't exist, but of course they do. So here's a good example. So an example is the integral from -1 to 2 of f of x dx, where f of x is defined piecewise as -x squared when x is less than or equal to 0, and it equals the square root of x when x is greater than 0. Because all of a sudden, this function, this piecewise function, doesn't make any sense. Doesn't make any sense to take an antiderivative of it, because it turns out it's not differentiable at x equals 0. But we can take an antiderivative of each piece, right? In some sense, the antiderivative should be -x cubed over 3 for x less than 0, and it should be that square root of x. The square root of x is really x to the 1/2 power, so it should be x to the 3/2 divided by 3/2, which is the same as multiplying by 2/3 when x is greater than 0. Right, because if I write this function out and I took a derivative, then on each piece where the derivative is defined, then I'm gonna pick up f of x. So in some sense, the antiderivative, right, make sure you guys know this if you're not watching the video. In some sense, the antiderivative is, exactly what I've written there. But we want to make sure that we can actually do this. So what do? Thus, we use property 5 above to give that this integral, -1 to 2 of f of x dx, is actually equal to, where should I split this up? I hope you guys can get an idea of where I should split it up. And yeah, you guys are definitely right. I should split this up right at 0. And then we just ask ourselves the questions of, what form does f take on that integral, and what form does f take on that integral? Well, f takes the form that it takes between -1 and 0. Well, what form does it take between -1 and 0? It's exactly x less than 0. So this is going to be the integral of -1 to 0 of -x squared dx plus the integral from 0 to 2. I hope you guys can figure out the other half of this. This is the square root of x dx. And we already have those antiderivatives. Those antiderivatives are -x cubed over 3 from -1 to 0 plus 2/3 x to the 3/2 from 0 to 2. And I can evaluate each of those separately as I plug in the top and subtract the bottom. So plugging in the top, -0 cubed over 3, subtract the bottom, -1 cubed over 3. Same goes here. I plug in the top, I get 2 to the 3/2 minus 2/3, 0 to the 3/2. So of course the terms of 0 are gone, and I'm left with 1, 2, 3, 4, 5 negatives. So this is actually a full-on negative 1/3 plus 2/3 2 to the 3/2. And 2 to the 3/2 doesn't really have a nice answer. Just leave it at that. But that's how you would do something for a piecewise function. That's the whole reason why we have this last case here. If a is less than b is less than c, then you can either add integrals together or break them up. And it turns out more often than not, we break them up. Okay. So something else I wanted to talk about, this is changing bounds with U substitution. So what I mean by this is, let's just do a very basic example. This is maybe my favorite example. Let's do the integral from negative 2 to 2 of 2x e to the x squared dx. Now, if we wanted to take an antiderivative, everyone would say U substitution is needed. And so we're going to do U sub, and I chose this problem because the U sub is relatively straightforward. Every single time you do U sub, I'll just write this down really quick. We are always trying to find both a function and its derivative inside the integral. In some sense, this is U sub in a nutshell, is that we're trying to find both a function and its derivative inside the integral. So in this case, can I find a function and its derivative? Yes, I can. So in this case, x squared is the function, and 2x is its derivative. Or in other words, 2x dx, or whatever you want to think about. So what does that mean? That means that the function is u, and du is the derivative of the function. So u equals, that almost looks like an a, I'm going to fix that. U equals x squared, which means du equals 2x dx. And we're off to the races, because what does that mean? That means that this integral, the integral I actually want to find, well, what is it equal to? It's equal to e to the u du. Hopefully you're getting far enough along with U sub that you can figure out that those pieces together are du. And that here, this is u. But this is the special part. This is what I meant by changing bounds with U substitution. Is I can't, let's say I'll do something wrong first. These are not correct. Right? Because those numbers are dependent upon the variable x. They're for the variable x. And we have the variable u. So we need to figure out what the new bounds are. The new bounds, it's not difficult to find them, You just have to remember that we do it. The new bounds are, well, you just plug U, we can think about as, I'll call U bottom. This is just the X value on the bottom. This is X bottom squared, because U equals X squared. And U top equals X top squared. So what is that? U bottom, X bottom squared is -2 squared. U top is X top squared is 2 squared. And so it turns out that they're both 4. And you guys are like, wait a second. If they're both 4, not -4. If they're both 4, then what does our property 1 above say? I'm going to scroll all the way up there now, so hopefully you've written this down. Property 1 up here says if the top and bottom numbers of an integral are the same number, then it equals 0. So why in the world would this integral equal 0? The integral from -2 to 2 of 2x e to the x squared dx. Why would that equal 0? I'm going to draw a quick picture of what it looks like. So this function looks something like this. Oh, sorry, that's e to the minus x squared. It looks something like, I guess really just something like that. And if I'm going from -2 here to 2 here, then the area that I'm looking at it's really, really bad. I'm going to do it in this instead. The area I'm looking at is this area and this area. And this is something I haven't really mentioned yet. And that's that area below the x-axis is counted as negative. So if area below the x-axis is counted as negative, then this makes a lot more sense because we are integrating an odd function. That means it's symmetric about, rotationally symmetric about the origin. An odd function with equal bounds. That means the negative area is exactly equal to the positive area. I'll say that here. The negative area is exactly equal to the positive area. So that's why it's equal to 0. And so that's a really good problem right there. It teaches you a lot of things. Now I'm going to mention this now. You don't have to change the bounds with U substitution. With U substitution, and then there's a big if. If you don't have to change the bounds, if you switch back to x before plugging the bounds in. So that's just the important part. So you don't you don't have to change the bounds if you switch back to x. What would that have looked like above here? If I switch back to x, I can integrate, right? I had gotten my point to negative 2 to 2x e to the x squared dx equals integral e to the u du equals e to the u d, sorry, no longer a d, equals e to the u, and I'm going to forget about plus c for now. This is e to the, what was u was x squared. So this is really e to the x squared, and now I can evaluate at negative 2 and 2. And this lets me evaluate e to the 2 squared minus e to the negative 2 squared, which gives me e to the 4th minus e to the 4th, and lo and behold, it's still 0. So that's another way you can do it. Just make sure you switch back to x. So you use it as an intermediate step. So you have it, but then you switch back to x there. It's up to you which one you like to do better. I actually do the one where I switch back to x more often because I don't like the extra step of having to figure out u bottom and u top. But I'll just write this down so that you guys can remember it. A quick one, how to actually change the bounds. So if u is some function of x, that's very normal. That would be like du would be like g prime of x dx. Then just what we had before, u bottom is g of x bottom. U top is g of x top. So that's all how you want to think about it if you're really confident you want to do everything in terms of u. I mentioned this because one of your homework problems says you do it in terms of u, so you should at least know how to do it once. But aside from that, I always like switching it back in terms of x and then just plugging the bounds in. So there's one homework problem that I know you guys are going to struggle with just a little bit. And so I want to cover that problem here. Covering tough homework problem. So this homework problem is we're simply evaluating an integral. In my case, from 5 to 7. Of 8x square root x plus 1 dx. And the problem gives you a hint. It says hint, let u equal x plus 1. So let's do that. Let's let u equal x plus 1. And the reason why you're going to choose this is that, I mean, indeed, as always, u is the piece in the parentheses. Like that's not gonna do you any wrong. This is indeed 8x parentheses x plus 1 to the 1/2 power dx. So indeed, as always, u is the piece in parentheses. I'll write that down here. As always, u is the piece in parentheses. And I mean, I realize that we had that, that nice list of when u should be certain things. The priorities for u. And over time, you just get used to which one you should actually be. But in this case, you would go down that priorities list, and yeah, it's the piece in parentheses. So if u is that, then du is just going to be dx because 1 is disappearing. So let's just rewrite it like that and see what happens. This is going to turn into And that's the whole point of this problem. It turns into 8, and we don't know how to handle that x. And then we have u to the 1/2 du. This is why I knew you guys would struggle with this. What goes here? So just take I don't know, I'm going to give you 10 seconds. Think about it. Is there any way we could figure out, because originally this was x, right? So originally that piece was x, but now we want to know what goes there. See if you guys can come up with that. Just think about it. Do you see anything on the page that can tell us what x is equal to? Maybe, some of you. This expression is equivalent to me saying u minus 1 equals x. Right? I've just subtracted 1 from both sides. But now all of a sudden I have something in terms of x. I say x equals u minus 1. I'll rewrite that. Instead of saying u minus 1 equals x, I now say x equals u minus 1. So that x up here, this x, is u minus 1, which makes that u minus 1. Eight u minus 1, u to the 1/2 du. And I tried to emphasize this best the last Friday. You want to simplify these antiderivatives before you actually try to take them. Or in some sense, when I say simplify, I just mean expand, usually. So there's a minus sign here. You can split at the minus sign. So you split this at the minus sign, and what do you end up with? You end up with the integral, really 8 integral u. It's u times u to the 1/2. So that's u to the 3/2. It's an ugly 3/2. Okay. Du minus, and now it's 8 u to the 1/2 du, because -1 times u to the 1/2 negative. Okay. And these are easy power rule problems. 8 power rule, u to the 5/2 divided by 5/2 minus 8 u to the 3/2 divided by 3/2. This gives me, dividing by 5/2 at the same time as multiplying by 2/5. This gives me 16/5 u to the 5/2 minus 16/3 u to the 3/2. And we're almost done. We want to convert back in terms of x. If this is a definite integral, right? Unless we want to change our bounds. We can change our bounds, or we can convert back in terms of x. And I'm going to convert back in terms of x. So u is x plus 1. We can see that at the top there. U is x plus 1. So if u is x plus 1, then this is really 16/5 x plus 1 to the 5/2 minus 16/3 x plus 1 to the 3/2. And this was indeed a definite integral. The whole time it was a definite integral. Our bounds were 5 and 7. So I plug my bounds in. One last step, 16/5. Plug a 7 in, I get 8 to the 5/2 minus 16/3, 8 to the 3/2 minus, and then it's this whole big chunk. That's always what I want to remember, is to put extra brackets around things so that I remember to distribute minus signs. 16/5, 6 to the 5/2 minus 16/3, 6 to 3/2. And most likely the computer will be able to accept an answer given like this. Otherwise, you can go ahead and try to get it simplified, but it's not going to simplify great. Apparently it simplifies okay, but not great. So I would just plug it in like this into the computer and then just hope for the best. But yeah, that's today's lecture. So you're just getting used to doing more and more complicated definite integrals. Of course, they can get basically as complicated as you want. Of course, you can always add more and more onto it, but I'll be nice to you guys on the exam. This is what it is. I hope you guys are all having an okay coronation. Mine's pretty good. I'm keeping healthy. I hope you guys are too. So with that, have a good one. I guess I'll see you tomorrow. Bye.